In this video, we examine the role that buoyancy plays in thunderstorm forecasting. Thunderstorm requires three ingredients to come together. The first is moisture to form the cloud. The second is instability, because we're looking at forming convective cloud. And the third is a lifting mechanism to enable parcels to reach their level of free convection. And wind shear is also important, but we'll develop that in another context. So here we have two traces, and we're looking at the potential for surface-based convective cloud. On the left, we have instability, but we also can see that the values of dew point are very, very low, so we don't have sufficient moisture to produce cloud. On the right-hand side, you can see we have sufficient moisture with very high dew points, but the environment looks quite stable. And so the sample cloud saturated adiabat, indicated in grey, is to the left of the temperature trace, and so clearly this is not a convective cloud situation at all. So we need both moisture and instability. If the parcel is unsaturated, it will follow the dry adiabat. Conversely, the dew point will follow a constant mixing ratio line. Shown in this figure here is a temperature profile and the mean mixing ratio for the lowest 50 hectopascals. And this is the value that will be used in convective calculations. So we lift the parcel along a dry adiabat and along the line of constant mixing ratio, and we arrive at a condensation level. When the dry adiabat crosses the constant mixing ratio, the air becomes saturated and convection commences. This is the level of free convection. And if the parcel remains buoyant, a cumulus, towering cumulus, or cumulonimbus cloud forms, because the parcel is now going to proceed along a saturated adiabat. So as long as the environment trace is on the cooler side of the lifted parcel, that is, the parcel is warmer than its environment, then we have sufficient instability for convection. And convection is simply defined as parcel ascent where no forced lifting is required. And so you can see as the parcel rises along the saturated adiabat, cloud of the convective variety can form.
NASA scientists have tracked gravity waves traveling thousands of miles across our atmosphere in concentric rings. Large storms can create these waves, which grow and spread upward hundreds of miles above the Earth's surface. The AIRS instrument on NASA's Aqua satellite detected gravity waves in the troposphere and stratosphere 12 hours before a deadly EF5 tornado in Moore, Oklahoma in 2013. On the instrument's next pass, 11 hours later, it detected even stronger waves. We pull up 250 miles to the ionosphere, where the waves can be observed by GPS satellites. Here, gravity waves are shown in greens and yellows, like ripples in a pond. The waves in tornado were both produced by a long-lived storm system. Understanding the spread of gravity waves improves global weather forecasting and space weather forecasting.
Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures.